Hello everyone, welcome to another stream. How we doing? How's it going? So last stream we got started on did we? So we finished off an outline of another shade of one of the shaders, and we started on a new shader. So overall I think we've got 5 shaders in our LOD and cluster construction, and that's all of them that we're going to need. But we haven't really finished them, and I'm hoping to finish them today. So it's taken a lot of testing out. Basically, it's a lot of code we've written. So it's about where was it? Yeah, it's about around 400 lines of code. Plus we've got this plan I've been working on as well. So we're just in this sort of step 2 here, LOD and cluster construction. But after today's stream, we should literally just be able to start plugging each of these shaders in one by one, because they happen one after the other, and looking at the data and see how it all went on. So what this shader's finished, which is called make persistent, which just basically copies the tree from this sort of like temporary place where we're building it, and we're going to copy it to a more persistent space, which is more compact. Whereas the build space is basically like, this is the biggest the tree could be, and we're just going to build inside that space. And then this final one is going to copy it to a more compact memory space. So we want to start on this shader first, which is called downsample occupation map, which is going to be nice and easy and be a bit of fun because it involves bits and bobs, you know. Oi, oi, Danzy, how's it going? How you been? Happy New Year to you, sir. Hey there, Kraz, good to see you. Happy New Year. How you both been? How you both been? So here's the scribble, which can help us make sense of the code we're writing. So we've got a bit set. Got a bit set. And it's a 4x4 by 2, which means it fits into a 32-bit integer. And so this is like one slice of it, right? 16 bits. The other 16 is behind it. And we've got 3D texture of this. So there's one to the right of it. There's one to the bottom of it. And there's another one behind it. So what this occupation map does is it basically tells you if a cluster, each bit tells you whether or not a cluster is fully occupied with 8 spheres inside. So we use this information while we're building to tell if we're completely surrounded by clusters which are fully occupied, and if they are, it means we can we can be a lower level of detail. So we just want to be able to downsample this because we create it in this shader here, right, at the highest MIP level, and we just need to downsample it to the lower MIP levels. So we'll run this like n times, right? Or n minus 1, right, where n is the number of MIP levels we have. So essentially, this is the unique data. There's 2 things that we have to be aware of. This is the unique data, and this is a repeat of the one from the bit set, from the unique data from the bit set to the right of you, right? So imagine this whole thing, this whole grid over here. but it will be talking about this specific part on the left-hand side, right? This is a copy, a repeat of that, right? And the X here will be a repeat of the one over there, right? And so on. This one is the repeat of the one below, and this one is a repeat of the one diagonal, right? And then obviously the whole back, the whole sort of 16 bits behind it, on the other side does the same thing. Wait, is that right? Yeah. Yep. So we have to downsample this. So to downsample it, we just take the 4 bits, right, and then that goes into that left bit there. These 4 bits are going to go into this bit here. These 4 bits are going to go into this bit here. And these 4 bits are going into this bit here. But you've still got to fill in these bits. How do you do that? Well, you have to remember this is from the right hand side one. Originally. But yeah, so the right hand side isn't going to be... Ooh. So I wonder how we could do it, right? What's the best way? Because traditionally in a downsample compute shader, you just get, you dispatch. Well, you can dispatch over all of the bits. You could do each thread gets a bit. Yeah, so typically you would dispatch over all of so you're going from a higher resolution down to a lower resolution. Typically you'll dispatch over the lower resolution. 4x4x2, so that's 32. So it fits into wave 32. But that's in pixels usually, and pixels are addressable. Whereas for a bit set, the bits aren't really directly addressable. So when you do that, if you go over all the bits, yeah, but we have wave intrinsics, right? So we can build it locally, all of them together using like the intrinsics, right? The wave intrinsics, and then do a single write out to memory. Yeah, so we'll do one bit set at a time. So effectively we're just going to do one write. I think that's the best way to do it. So you do one write. There'll be a boolean to be like is set. Right, we'll get that one. So this will be known as the source. Occupation map source. Sorry, destination, obviously. We'll be writing into... So each wave gets a bit set. Each thread within a wave gets a bit, right? So the coordinate is going to be U32 times 2 SV dispatch group index .xy, and that'll be, yeah, that should be perfect. So you basically just do that. Oh, it's times 3, isn't it? It's XYZ. And then you write your bit. Oh wait, sorry. This you need to save with the first one within dispatch local index.x. Wait, that won't work, will it? But yeah, dot x equals 0. And works right like this, right? All equal so if they're all equal to 0, x, y, z, then we are the first thread, so we can do the writes. And we're trying to get, but here you want to do that sort of wave intrinsic, right? So this will be the bit set. So I think we should be able to use wave. Ooh. Is it ballot? Do I have a ballot? Look at my intrinsics. I don't think I did a ballot. So what sort of wave intrinsics do we have? So we want it to return a 32-bit integer, and we want to take in a boolean, right? Where it's going to give us a bit set for each wave. I think that's a ballot. You could do an OR, a bitwise OR, and know your index. That's another way around it. Yeah, we'll do that rather than adding more intrinsics. You just do this, right? One shift left. So get your wave index. Z times 8. All right. Was it 16? No, what is it? Oh, no. Yeah, 4 times 4 is... You have 2 Zs, right? So you use the 4 times 4, that'll get you a slice. That'll be 16. So then it'll be plus... times by 4, which is the width, plus x. So that's flattened out. So that's a thread index. So you want to say is set. We shift that into position, and then we do a wave OR. So all threads that run this in lockstep, there'll be 32 of them, enough to fill up this bit set, right? And they'll all put all of their bits together. The first wave, the first thread, is going to go here, and this one will do the final write out to memory. So now all we have to do is write this piece of code now. So this piece of code so we've got to take 4 bits, right? Well, that should be a store. Good. Yeah, so you need to do a load. I don't think there's a way around it, but you want to load like a source bit set. And so you load that from the source one. The coordinate that you're loading from, so you'll need to take you'll need to use the coordinate. That's the destination coordinate. The source coordinate is destination coordinate multiplied by 2, right? Because we're down sample size is also obviously it's half every time, right? Then so now you've got to figure out how you sample from it. Sorry, how you get the bits you want. You gotta get 2 by 2 out of there. 2 by 2 by 2, isn't it? 2. Yeah, also there's a 1 pixel border we'll worry about actually. Hello, Rosmosco. Isn't it 2 per dimension? Lid. Oh, wait a minute. Yeah, maybe. Yeah. You've got to do 2 by 2 by 2 every. Yeah. And you got to compress that down, isn't it? Yeah, that's right. Yeah, 2 by 2 by 2. So I've just thought about the other problem is we're keeping a 1 pixel border always. So this is obviously 1 bit set of the overall grid. But you imagine there's a massive grid and the edges are always kept empty. And the reason why they're kept empty is so when we pick up a sample location and we check the surrounding, right, to see if they're occupied, it would automatically fail this case, right? Because these guys will never be set; they're always left empty. Then that avoids having if statements to say, "Hey, if I'm near the edge, then don't do anything." Right? We avoid that if statement entirely, and it's all just driven by the data, right? So when we downsample, we want to keep that border. Bearing in mind that the border also exists, and we have to kind of ignore it. So there's that as well. So so we need like a this is the coordinate for the bit set. The first bit set. So if I multiplied it by 2 to go into the sort of one we're coming from, right? Because we go from the highest quality down to the lowest quality, so because we're downsampling, right? We're obviously going to have a 2 pixel border at the edge now in terms of the way we're addressing. Like, just to make this look a bit more obvious, we have a we'll have another one called we have a bit coordinate, and that bit coordinate would use the local index. Right. So we should probably, so in this case, we should probably just use the overall combined version of that. Times it by 2, then properly land it in the, yeah. So because we've times it by 2, we then need to take away 1, right, from all of it. Because there'll be, oh, why am I doing that? Because there's a 2 pixel border. Right. -1 as we have multiplied by 2, multiplied by 2, and there it, and as there is a 1 pixel border, we keep empty. No, 1 pixel, 1 bit border. Did I call it pixel and the other stuff? We just called it the empty border. Yeah, 1 bit empty. Maybe I should call it 1 bit empty border. Right, that would be good enough. So there's a 1 bit empty border. -1 as there is a 1 bit empty border. But we have multiplied by 2. Border which we don't want. Okay, so that means which we don't have. Right, okay. So then we take away the 1, and then that means we should be addressing correctly. But we have to, so we should call this bit set coordinate. Okay. I didn't kind of think, but so I'm wondering if if these are repeats, if I'm just reading from if these are just repeats of the bit set from the right over here, right? Okay. Then this will be downsampled into here, right? And then that would be the one from here, which would also be the one from over there. I think that's fine. But keep doing this. So the right hand side is going to have like an empty. Quite a lot of empty. It's going to have an empty side to it, actually, thinking about it. So we might not need an empty border. Yeah, maybe. Oh. So we've offset everything anyway by 1. Huh. See, I wonder if I'm populating this in a very weird way. Because I think with on the furthest right hand side and the furthest bottom side, or whatever way you're thinking about it, if this is the unique part, this is the repeat of the one to the right and the one diagonal on that. When you get to the edges, this is going to be wasted. Not that it matters that much. But we offset it by 1 anyway for the border, right? At the start. So this is all empty at the top left-hand side, or whatever way you look at it. Maybe it's bottom left, I'm not sure. But anyway. So this, like... So I'm curious whether we could have organized it better, really. So this is where, like at the end of the day, when we try and go and sample from this thing, we only have our sort of center location in this 2x2x2. And the reason is because when you have your sample point here, you check all the neighboring guys, right? And if it's not in these guys here, it'll go out of the bit set, and then it requires 2 or more than 2 samples to work. So I'm curious if we initialize, because it might make the downsampling a bit easier, I'm not sure. Yeah, so the first one, no, And then we sort of copy that. We copy that back. We copy those 2 back. Whereas if we did it here, if you set a bit here, you have to copy that back to the previous one, which puts it like in the previous ones here, right? How are we writing these guys out? Address sensitivity. Yeah, maybe it's fine. Yeah, let's just roll this way for now, because we've kind of written it this way. But I'll think about that some more. Right, so let's just carry on. Yeah, so we're trying to sort of address it now. The down sample. So, that goes there. So you need to work out the bit set coordinate. So that is going to be divide by 2. I think it'll work out right. Yeah. So 2 by 2 by. No, because when we're reading from it, yeah, I think when we're reading from it, we address it in this case as a 4 by 4 by 4. So bit set coordinate, then bit coordinate within the bit set. Yeah. So now we just got to get 2 by 2 by 2. So to get 2 by 2 by 2, we first need to work out how is that represented in hexadecimal, basically, and then we'll shift into place. Is that right? Wait, we need to get 2 by 2 by 2. Oh, damn it. I wonder what that is. Let me see if I can pick it up. I'll turn up my volume really high. So which way is it? This way? There we go. Alright. Yeah, that noise there, that's the actual microphone cable itself. Let me put something else there and that'll fix it. Whoops. Yeah, it's quite difficult to solve actually. It's just kind of hanging off the table. Yeah, I wonder what I can do here to fix that. Right, I've just removed it from the thing now, so hopefully. Hopefully that's better. Let's try that. Now what I can hear is the springs. Is that better? Awesome. Thank you. Yeah, it's a bit of a pain. I should really try and get a setup where I put the microphone stand connected to like a wall or something. Because, yeah, give that rest of the music back. Let's adjust those levels my end. Excellent. Right, so how are we going to address this thing when we downsample it? Like, ideally, we need to address it as a 4 by 4 by 2. We still address it as a 2 by 2 down here, though. Right, so if we address this as a 4x4x2, you basically want to take this one and then put it into this one of the destination, right, the lower resolution. And this one goes into here. No, you're addressing it as a 2x2x2 then. Say we've got this coordinate, right? Or this one here, this one would be better because it's not 0. So you got one along the x. Right, we multiplied it by 2. We took away 1. Because that 1 pixel border. Hey there, Captain Chica, how's it going? It's been a while. How you been? So 1 times 2, which would be 2, right? We took away 1, which then makes it 1 because of the 1 pixel border. So it puts it back there in a sense. And then, so we've got 1 along the x. Then you mod it with 2, obviously you get 1. So yeah, that's right, isn't it? That's the right offset you need in a 2x2. Right. So if we build a, get this right, it's C, isn't it? C it gets me 2 bits, right? 0, 0. Then another C. 2 bits, 0, 0. Then you want 0, 0, 0, 0. Yeah, then you want 2 more zeros. Then you want the same thing for the behind layer as well. So it's C0, C0, 0, right? I think that's right. And then we shift it into place. So you need to shift it. I think that's right. Let's just double check my my bits. Do I know my bits? Yes, it's C. So in a quad, when in a nibble or whatever you call it, it's yeah, the higher bits of the nibble. So what we've got is a C, C. So you wrap those around to the next line, right? So they're next to each other, right? Perfect. So in 3D, that's a on a 4x4x2. That's the 2x2 of the top left or whatever way you look at it. Then we need to shift into place. So you need to shift it based on, I did it earlier, so it's, oh shoot, that's a copy paste error. Look at me go. Wahoo. Amazing. So it's shift into place based on the Y and the Z. So yes, bit coord take away 1. That's good. It might be different. Times by 4, I think it might be, but we'll see that in a minute. Then you want to add source bit coord.x. I don't think we care about the Z. Yeah, there's still something we've got to correct up here. Just got to think about it a little bit more. But that's going to give us the sort of the bit set. This is going to give us like the pass bit set, as we're going to call it, right? Now we need to. So is set is if the source and the pass bit set is equal to the pass bit set, right? And that'll mean that we can downsample. So that means that mask of 2 by 2 by 2 is all on. And if it's all on, then it means our single bit can be on in the downsample version. Cool, so that's the basic idea. We just got to make sure it's all correct, and it's not at the moment. Was busy implementing Nanite. Whoa. So you got your little compute shader rasterizer. Is it going brew? You know, is it going fast? How did it go? Give me the spiel. So so I don't. Are we dividing by 2 across all the axes? Right. So let's run over this thing again. Where this addressing is weird. Okay, so you got your source coordinate in the higher, sorry, in the lower resolution. We multiply that by 2. My mouse has just stopped. There we go. So multiply that by 2. So let's say we're trying to get this bit coordinate here. So this would need to be a repeat, right, from the bit set next door. Yeah, I see it. This isn't. So this, okay. So remember, this is a repeat from the bit set next door. All those bits. When you downsample it, this one goes here, right? So this one, when you're talking about this bit here, right? This actually comes from. Yeah, I think I've done the addressing wrong. So this one, so these two come from, yeah, the first bit set. But this one, it won't be on. Like the current code is going to try and get it from here, but technically it's here because of the repeating nature of the bit set. But technically it comes from the one over here. So the way we should probably address it is just ignore the repeating guys and skip over them. And that's the way we need to basically worry about it. So when we're trying to work out our bits, so you're trying to work out this one, right, along the axial 2, which means you need to go to this the second bit set overall, right? So if this thing is, so there's a 1-bit border. That's the other thing, is a 1-bit border. Yeah. Hmm. Yeah, that 1-bit border is messing us up real bad. When it comes to this. That's a good way of solving it. Okay, so this is the store that when we create the map initially. So we... The highest LOD cluster coordinate, we add 1 for the border, then we divide by 2 to fit it into a mod. So we'll never land on the 0, on the 0 border, right? So it's going to write into the first. So 0 is going to write into here, right? 1 isn't going to write into there in any way. It's going to write into the next bit set, right? At on the left hand side, right? Because when you write into these two, and then this is going to write back into here as the repeat or something, here, right? Then it writes back into the repeat there. So it does end up writing to here eventually. But there's still this 1 pixel border. So with the 1 pixel border there, yeah. So this is fine. This code is all fine. But when we do the downsample, we need to probably address it. Like so the 1 pixel border right. So imagine we start from here. From here, and for here we're going to need these two from the higher resolution one. This one is going to need these two, right? No, it won't, because it's a repeat. This is the annoying thing about it. Yes, this will take this one. This one, will it just take the one from the next bit set? I think so, right? Yeah, because it'll need these guys. Yeah. It's the same problem. This is excellent. So we've just got to offset it. So that's really easy to do. So this means that your dispatch index, okay, this will work. So you've multiplied it by, so whatever your dispatch index is along the X, it's just that that's the bit set you're indexing. That's the way it needs to be taken, I think. So that's the bit set you'll be indexing into. And the coordinate is always, because it's repeated, the coordinate is always just the one in the middle. And we just need to check there. And that's it, and that includes the border problem. So we don't need to do anything like this. We simply just need to get a mask at the ready, right? So let's see if we can get the mask. See if we can program that ourselves. So the top row is nibble is 0, right? Second one Oh, this one's funny. Is that so? Obviously, 1, 2, that's 6, right? Am I right? Oh yeah, 6. And then it'll be another 6, and a 0 for the bottom row. And you need that again for the other side, the other slice behind it, so 0, 6, 6, 0. So that's the past bit set, and that's just wherever we're set. That looks stupid easy now. But that might be it. So the repeat has maybe helped us with a down sample as well. Not that it's just simplified it as all. So let's just double check that, right? So you've got this is the border on the top left hand side or whatever. This is the one we're trying to get in the new lower resolution. So in the high resolution, it wants this part from the first bit set, right? So that would be am I right by calling it dispatch index though? So you'll be 0. I've not offset anything here. Yeah, the way we're setting it here is a bit weird as well. It's not accounting for the border, but let's just make sure we know if we're set or something. Let's just make sure we're addressing right first, and then we'll correct that. So 0. Oh, it's bits in the bit set, isn't it? Yes, each one of these gets a thread in here. So I think we do want to offset it by 1 for the border. For the 1-bit empty border. So if you've got this one here, it's offset it along the X, Y, and the Z. That makes sense, right? So you'll land here, technically on the slice behind. You will then what else? Yeah, so that's the bits that you're getting it from. So this will go and say, hey, I want to load from that bit set, and then look at its center, and then if its center is fully set, then I am set. So this one here, right, we'll need to go to the word, or we'll need to address in the higher resolution one, right, next door. Paya, thank you so much for the sub. Appreciate it. How's it going? 28 months. Look at that. It's over 2 years. Fantastic. How you been? How's the New Year treating you? So we'll need to, this one, right, it starts off at 1 on the X, right? But then we add 1, then it's 2. Oh. We don't want to add 1. Yeah, we only add 1 for the sort. Almost, yeah, it's good. So this would then, it would get it from this bit set, and it gets it from the middle, right? Which is this part of that over there, right? And that's fine, because in the higher resolution, That's the equivalent of getting... So the first, this one here, got these two from the higher resolution. And this one here gets these two from the higher resolution. But remember, these are a repeat of this. Wait, I've done it. This is not to scale. They're a repeat of that. This is 2. Right. 2 by 2. So we need these 2 by 2, right? And that x there is this x here. Excellent. So this is a repeat of this here. That makes sense. And that will keep going until the end. So, yeah, I think that works out. So this is fine. This is not fully fine. Nearly there though. So this is fine. Right, thread index is flattening that out. This is also fine. So it's taking every thread, so each pixel within the yeah, wait a minute, did we check one? I need to just quickly double check. And one more time. So that will do this one over here again. Yeah, which is the same as bleeding into there, that's fine. Then they'll just step over and keep going as it goes right or down. Okay, all good. Oh, so this one here then, so this just combines all those bits from each thread into a single, it shares them across all, into a single bit set basically, across all threads. Here with the first thread, now I need to store it into the right place. So I think that is right. Yeah, we've accounted for the border, right? Hmm. Oh crap, we might have not accounted for the border in this bit set. So I think this storing code is right. Damn it. Surviving. Hope you had some good holidays. Yeah, it's been pretty good. Mostly just relaxed, chilled with the baby and the wife. Did some shopping, saw family. Eating tons of food. You know, standard Christmas sort of stuff. Yeah. Hey there, Claus, you honey. How's it going? Welcome back. Yeah, it's been good. Also played some games as well for a bit. Got to actually play some games, which is good. And yeah. So I guess before we can finish this storing question, I've got to fix actually the way we're storing it in this bit set. So sure, you said, hey, what is this one going to be set to? And then we added one because of the border. And this is only when we're sampling it. But this is not how we're storing it within the bit set itself, right? Because you're going to look at that one. It is. That's made it perfectly fine. So for this thread, it's going to look at this one. I've maybe done it the wrong way around, right? So it's going to look at this. We could just put an if statement in, right? It's not a big deal, but it's always do it without an if statement. Like, ideally you want the first... Like, he'll look at that, isn't it? Basically. So the first thread is going to have this guy, but that's on the border. And we said, look here. This one's also on the border. This one's on the border. This one is not on the border, and this is the one that you want to actually check this information for, right? So all the other ones need to come back by one. So we probably want to just say we probably don't actually add one at all. We probably want to take one actually. But then the problem is you'll underflow, right? Because this is an unsigned. So what you got to say is if, we'll just put an if statement in, it's probably going to be pretty quick anyway. But it's going to underflow. So you do the whole sort of any bool. Any equal e32 times 3 dispatch. Well, it's not even that. If any of that is equal to u32 max, then you're automatically not set. Branches. Something like that. Yeah, so we'll just take away one. And I'll go to there. And then look at that bit set entirely. Right, all good. Okay, so that solves the problem of populating the bit set just fine. Now it's just a case of storing it. I think that's fine, right? So it's the group index. Yep. Okay, that's it. That's the downsample shader. That was pretty weird to think about because they're repeating data, but that's pretty cool. So the next thing we need to solve, yeah, okay, so this would basically be called for every MIP we have, right? So I think we're doing a 256 cubed. We're doing a 256 cubed area, so whatever it takes to get that down into like a 1 by, or a, whatever it is, a 4 by 4 by 2 or something like that. Yeah, we'll work that out when we try and call it. Awesome. So the final shader we need to finish is this one here, which is called make persistent. So what we have is a nice little bit of memory. That's a really big chunky piece of memory. What I mean is a nice long piece of memory. So essentially it's an array of nodes, right? And it's actually like far many more cells than this. But the basic idea is we have a cursor smack bang in the middle, maybe in the middle, but maybe actually a bit to the left or whatever, I think. And the idea is that all of the leaf nodes sit on the left-hand side and all of the non-leaf nodes sit on the right-hand side. So this means when we fire off a compute shader, well, the reason why we want this is so when we fire off the compute shaders, we just need to say, hey, I want to talk about, I want to dispatch for this volume, and I know where this volume starts, and I know it has this many leaf nodes, therefore I can start from, I can dispatch, if I want to go over every single node in the tree and start from the highest level of detail, I can start from the leaf nodes, which are the highest level of detail, by assigning a thread to each of these guys. And then we can check them and see if they're on the screen or something like this. But we actually use this while we're building it as well to do a check on how we can sort of simplify it. But yeah, we do something like, you know, can this thing be simplified, or we say, can this thing be drawn on the screen? And if it can, we basically stop there, and in the case of binning, we bin it into a screen bin or something, you know, a screen tile. But if it can't, then it will daisy chain up into a non-leaf node and repeat the process again until it's found the thing. So that's the basic idea with this guy. Is the make persistent thing itself has been launched across all of those leaf nodes, and this is in the temporary build space, where that is a nice big chunk of memory, enough to hold any our maximum sized volume. And then we wanted but what we've done is we've measured in a previous shader how big it actually how much space it actually takes. And we've then allocated that chunk of memory somewhere else. So what we're doing is we're going over all of the nodes now, and we're just trying to see, is this one we need to keep? If it isn't, we go up to the parent and we check again. And when we find one that we need to keep, we copy it into the persistent piece of memory. So this is basically the code. This determines whether or not we want to keep it, if it has any children or any spheres. And if that's the case, we keep it. So basically, there's an array of cluster nodes. We probably want to also pass in some form of, this is the destination. So this would be the new cluster tree midpoint cursor. So that's that midpoint where before is the leaf nodes, after is the other things. So what we need to do when we set this thing off is we could probably, see, I don't know why we're storing it in the volume. We could probably have it in our global data structure and then set it properly. Yeah, because we're sort of setting this leaves count and stuff like that. I think these should be set here. Okay, so here's what we're going to do. We have this global data structure where all our globals go. Isn't she beautiful? So we're going to add another sort of place. This is going to be for our builder. So this is our, we could call it like the cluster, I don't know. Anyway, it doesn't really matter so much what it's called. So you just need to know, you need a midpoint cursor. So we put some comments down. This is how we're sort of like used when constructing a volume. So this would be, you then want to have the number of leaf nodes and then the non-leaf nodes, and this is what will atomically mutate, right? So when we reset our volume, so I was initially thinking so rather than calling volume reset, which probably splits into two, right? This would be called volume constructor reset. So this is going to reset the constructor and not the volume itself. So we have where the midpoint cursor is. Yeah, but that's not passed in, that's a global. So that'll just be global. So we pull that boy out, and then we do our sort of access and then write out the node. So we could do this a different way. We do like, I don't know. Yeah, I think that's ideal. So that resets the, this just sets the root node basically. Maybe it should do some more stuff. But this volume reset, this should happen right before this sort of make persistent thing we're doing, right? So this is where, so we'll get back to this in just a second. We just need to finish patching all the previous code. Not too long. So when we try and patch the volumes, so here, this is in the initial part where we construct the tree. We need to address the global here. Right, so you do globals, and this is reaching inside the globals buffer, right? Volume, this is the leaf one, or does this one be the non-leaf? Right, I'm not sure how many of these we have, mutations that we have. So are we even reading the volume at this point? I don't think we should be touching the volume at all. Let me just quickly double check that. But when we're constructing it, right, surely we're not touching the volume or anything else. We're touching it just for the midpoint cursor, right? There's probably more things we need to set that I'm missing, like the maximum size of this thing. I don't know. Yeah, we've not actually touched the volume. So So the volumes only need to get set when we are actually making it persistent. And other than that, it's just editing the nodes buffer basically and the spheres, all that good stuff. So all this volume index stuff can just go. Except for volume reset, that one. Volume reset is near the persistent one, isn't it? Yeah, we're good. Right, it's pretty good. I'll have a look at that one. So right. So oh no, we didn't finish patching the midpoint thing. That's fine. So we're just going to search for volume, and we'll just basically delete and then replace it with the right stuff. So this one needs to come from actual global. So in this case, we'll just put it as some sort of local thing. We'll call it volume cluster tree midpoint cursor, and then we'll fetch that from global as well, like that. So effectively, whenever we're doing any of that, it's just some of that, right? Oh, did I? Ah, damn it. Volume dot. So plot that down there. Make persistent. Excellent, we're here now. So what we need to do, so some other place we need to allocate. I don't know how we're going to do the allocation yet. We'll do that when we're plugging it all in. But effectively, it's probably going to be in. So it shouldn't be in the push constants, right, that come from the CPU. Ideally. So I don't know if we need a. I don't know if it's allocated on GPU. It must be, right? If we're doing this all on GPU, the GPU. Well, no, you see. Like, the CPU could keep track of what's. I was thinking. I was thinking that the volume, when you read it from the disk, it knows how much memory it's going to take up, but that can change if the game gets updated and we fix a bug. But so when you sort of like build these volumes, we need a way to allocate the memory. How are we going to do it? So there could be like a heap allocator, like a free list heap allocator on the GPU. And we could probably do one of those sort of like, we could probably make it like O1, right, where it's just an index away and it just grabs it from like a power of 2 bucket or something like that. But then you basically waste memory. You could do other things, right? There's probably other strategies. But you just want like a linear list of nodes. But could the CPU is probably better at doing that than the GPU is. Well, actually, the GPU, it doesn't matter. Actually, because the GPU could just launch tons of threads to solve the problem. Yes, it doesn't matter. Where's the data best held? Because the CPU ideally needs to know, like, hey, before I bother, well, the CPU can just be like, well, we can try to construct this volume, and the GPU can just tell you if it succeeded or not, basically, and then the make persistent final one where it finalizes everything could just be a dispatch indirect and it just doesn't get launched, right? That's one way of doing it. The other way would be the CPU knows everything and the CPU can then ensure that this thing is going to work, and then because of that you won't have any wasted frames where you tried to build something and then it didn't build. Yeah, something to think about. Definitely something to think about. But somehow, basically, let's just write some pseudocode. We need to set up a whole bunch of stuff. Midpoint cursor needs to be set to something. I don't know what it is. And this will be the destination. Place. We've also got to set exactly. Maybe this doesn't need to exist. So we've also got to set the leaf nodes count and that. So this will be set to 0 initially. We could probably set this at the end, to be honest. So, can we set it? Oh, we can't really set it at the end. So we've got to be using like volume. No, this goes in the reset code, doesn't it? Whoopsie. Whoopsie, whoopsie, I forgot that. So this all happens here. So we'll set that up there. Somehow it needs to get set. This needs to get set somehow. I'm not sure how it's going to do it, but it needs to get allocated. Yeah, something to think about. We'll let that be a compile error for now. Don't know where it could just be set in some global place, and we'll store it in another shader. Now maybe we can allocate in this shader. I'm not sure. Let's try that for now. These get cleared to 0 because we're actually going to allocate now. We'll just basically bump allocate these across all the threads. Grid dimensions. Yeah, we'll know that from the CPU side. Okay. So from the volume, we need to fetch this thing. And that'll just come... I don't know, that'll just be in volume. So basically we've got this sort of like source, volume, cluster, whatever. This comes from global volume, cluster, tree, midpoint cursor. So this is how we're going to be sort of climbing the tree from the leaves. And Then, okay. So you get your cluster node. You check to see if we want to keep this guy, because if it has any children or if it has any spheres, we're going to keep it. So this means we want to do that allocations, same allocation scheme as we have above here somewhere. Why up ago a minute? No, it must be in here. This is it. So there's your new node index. So your absolute node index. So this is going to be the DST. And then this is going to be ABS DST node index. This is equal to volume dot midpoint cursor plus DST, right? Something like that. Okay. And now you just need to perform the copy, and that should be pretty easy, right? So there's got to be some patching involved. But I'm not sure exactly what patching. Like, we need to patch the child nodes. Is that it? Is that only it? So this all stays, right? The child indices, node indices, are what need to be patched because they're no longer. So these are relative from the midpoint. And the reason why they're relative is so we can defrag. We can also defrag by reshuffling things around when we end up freeing volumes. Oh yeah. So I guess you only need to patch it. Like, I know my node became was kept, right? So what I need to do now is I need to reach into the parent in the build space, right? And I need to modify my child index. So what have I got? So yeah, one thread per cluster. Sorry, one thread per cluster node. But I need to know what my where have I done my mod 2s? Oh, here we go. This is it, right? Within the parent. Exactly. Yeah, I need one of these. Child index within the parent. So you just want to say, hey, if I'm not the root node, reach within that, get the children node indices, get and update it to the new DST node index. Okay, so we're going to say reach into the parent node that has not been made persistent yet. Reach into the parent node that has not been made persistent yet, and yeah, sort of like a point and overwrite the reference, the child reference to our node. So all threads will end up doing that. All threads will end up doing that, and the final thread, which the last child of this parent node that reaches here basically will be the thread which carries on and goes up to the parent node, and then all the other threads just terminate. Yeah, so that's how we solve the problem of waiting for all of them to finish. So I think this is fine now, right? Copy node to persistent memory, check. I guess we'll put the comment in. Just move the comment up. Copy node to persistent memory. And this thing is basically saying, reach into the parent node that has not been made persistent yet, and overwrite that child reference to this node. Cool. So this other one is saying, hey, we don't want to keep this, right? Node was not kept. So why might a node not be kept? Should we add a little bit more detail to that? So when we refine it, we try to remove it if the leaf node is completely surrounded by other clusters with a full set of spheres. That's the only time, isn't it? Yeah, it's the only time we actually try and delete. Yeah, but it's no longer a leaf node because you can keep doing it. That needs to go. Mark the child for deletion. This is probably deleted in the next shader, something like that. So we don't delete it in any other way, right? So yeah, no was not kept as it was a cluster that was completely surrounded by other clusters, and sort of a lower LOD was used, right? So now we need to deallocate that memory back to the that sphere memory. So how did we allocate the sphere memory? It was here, wasn't it? Great. Okay, it's just a stack. Excellent. So there's just a stack of 3 indices, and it's just a range of 8. So we just need to pop that back on. So we atomic add, we get this sort of slot. 3 index is a bit of a weird one. Weird name. More like a slot. So then you basically write that slot out back into there. So it's be node dot spheres start index, right? And voila. Away we go. So Yeah, that's pretty good. So we basically have an array. So we have one big array of, so there's 8 spheres per cluster, right? So 2 by 2 by 2. And you just need a contiguous block of spheres, right? Imagine that's 8. It's not really. So what we have is we just have one big buffer which has a bunch of spheres next to each other. And we have, and this thing here, this 3 indices array, all it's doing is storing an index to the start of a 8 in a row. And then obviously there'll be another one which stores for after it, right? And so on. And all we're doing is this 3 array is going to be pre-populated with 0, 1, 2, 3, 4, 5, 6, and so on. And we just pop it off the back with a simple operation of modifying this. So it's a nice and quick way to allocate the memory, basically. Just requires 2 buffers. So it's pretty sweet. So yeah, that is basically it. So that is the cluster construction. There's probably some tweaks we're going to have to make to these shaders as we plug them in. Like there's some unanswered questions about how we're allocating some stuff, or because they require deeper thought on the matter. And every time we're going to plug one of these in. So yeah, we're going to plug them in one by one. So first we'll get them compiling. That's the first step. Then we'll plug them in one by one and test them out. Make sure the input data produces the correct output data, and then just keep doing that. But every time we plug them in, we're going to have to check over the shader and just double check everything's fine, and probably adjust the comments, and all things like that. I forgot to change actually. Some of this stuff has to change now. We're doing 256 by 256 by 256, meaning we should probably change. Yeah, so let's make a compile first, and then we'll change it from a 1024 cubed space to a different one. Oh, what the hell's going on here? An extra bracket. Let's what have we done here? I'm so glad we're on the outward end of this. Such a big job. And I didn't know what I was building fully until we built it, so just one of them. But we get to get it working again. Why doesn't this thing work? Bracket pair, but got this, right? Ah, we've got an open bracket. No worries. Dun dun dun, found you. Cluster children count. Right, it's defined further down. How amazing. Yeah, we've just gone a bit messy with this code. So definitely before we commit it, we need to sort of like just copy it into the right place. Because I just started basically sketching out the data structures all in one place. So we've got how it's going to be stored on disk, right? How is it going to, like, this is all the stored in disk stuff still. This is it on the GPU. I was just sort of sketching it all out and how I want it to be. We'll go over some of this and get it compiling. Right, constructor reset. Huh. That's a good point. What is going on? Expected type name. We got identifier. What compiler is this? Is it my compiler? Yeah, it's my compiler. Expected type 9 by got identifier. What is going on? How stupid am I being right now? Okay. That's the data structure. What's going on? No, compiler, what are you doing? What? Should we reshuffle those? Because... So first of all, that is the wrong... we don't want this one. Anyway. I don't think we need any constants. But anyway, let's change it over quickly. Let's see if that's... I don't think we need... Yeah, we just need the cluster nodes. Damn it, it solved the problem. Okay, we'll just roll with that. I don't know what the error was about. What is this? Data LOD count. Where did that go in the end? Is the problem small v? Oh, it might be actually. Or a master, that's probably right. Yeah, sounds about right. Yeah, you're right. Oh. That's the wrong one. Oh, damn it, it's searching it on Vim because I've got the, or I don't care about lowercase. That's cool. Okay, thank you for that. I'm going blind, as you can tell. Yeah, that's not a good error message, is it? I should improve that. But to be honest, it probably falls in line with the standard C error messages, you know. They're like, it's not a C compiler if the error messages are understandable, you know. Like it's, I'm sure it's somewhere in the C spec, you know. If you scroll down far enough, error messages must be confusing and unreadable. The 10K a week type is to catch, yeah. Usually, yeah. Yeah, those type of errors, just, you could be lost sometimes for ages. I had one the other day at work where I did like It was the operator precedence thing. Got one in here, I'm sure about it. Yeah, I did something really silly and really dumb, and it was funny. I basically wrote some big ass expression. I did a long expression like this one, and I did like plus, you know, node index is greater than 3, right? And I was expecting that boolean just to be changed into like an integer, but really it's sort of, because of operator precedence, goes around like that, right? And then it's evaluating the whole thing to 0 or 1, and I got so confused I thought it was something to do with the type system. But yeah, so I needed to do that. Classic. I just found a good reason to have a case-insensitive language. I think, you know what, I think there is a language that does that. I forgot which one it is, but it does it even further. It does it style insensitive as well. And I forgot what the language is, but someone could probably say it. Yeah, it's style insensitive. Is that crazy? There's no LOD count at all. Must have deleted it. So we're actually gonna have 8 LODs, which we're gonna. So that would be 256, obviously, right? Yeah, I might limit it to 250 because that way we can do 4 mil times 250 and it reaches 1 meter. So we'll see about that. That way you can get perfectly divisible by a meter, and you can construct stuff in meters. You know, a nice good measurement. Right, so why is it still complaining? Right. I'm still confused. Is it the next line? What is going on? The construct LOD. Come on, that's not... Oh, okay. Okay. Copy paste error. Radius. There's no radius on a sphere? Yeah, the radius is fixed, isn't it? Something like that. Of course there's no radius on a sphere, so what the hell are we going to do? Because every sphere has the same radius. Voila. Caseness and lexes and parsers make me go from... Made me go from Microsoft to NeoVim to JetBrains. What? Crazy. Wait, so what made you go 3 times? You went from Microsoft, you know, Visual Studio Code, oh sorry, Visual Studio, right, to NeoVim. So I guess you liked it in Visual Studio, and then you sort of went back. You saw it had the same behavior in JetBrains, and you stayed there, right? Is that it? Yeah. So what? Why? I've been using radius this whole time as some form of thing. But we only set it to 0 anyway. What the hell am I doing? Alright. Got a thing to correct. So we're using this as a way to say whether the sphere has been set, or whether it exists or not. Right? So I guess we can just use LOD for that. And we set up LOD. No, because LOD 0 exists. Right, so what thing can we zero? Which should be, we'll have a bit in there. We've got bits, right? One more bit is free. Or exists. Something like that. So when we do radius equals 0, exists equal 0. If exists is not equal to 0, it is new if it equals 0. Good. Right. That's pretty good. This is in the old code. We can remove, don't worry about that. It's all commented out. Okay, so this part of it is to do with... So the problem is with GPUs is that, or the AMD ones at least on Linux, is they crash when you go out of bounds. And it brings down the whole desktop environment when you index out of bounds. On NVIDIA hardware and a more sensible driver, or maybe Intel does the same, you get a device lost. A Vulkan era device lost. So that would mean your game still crashes. So typically what you do is you basically you clamp it. For safety. But then it starts doing things which then it starts misbehaving. So the question we have to ask ourselves is, when we're constructing, like, you're constructing a tree and this tree has to be perfect, right? So if as soon as you go wrong and if you try and keep it going and it's wrong, like I'm just curious on you can end up in like infinite loops with really, really bad memory anyway if you have a wrong tree. So maybe we just let it crash. I'm not sure. And just fix the problem. But we could point it to like a very specific node, which is just unwritable or something like that. We have a special node at node 0 that we just treat as you've landed inside an invalid space, and this is we're going to handle this in a more elegant manner, right? That's something we could do, but it does add a bit of overhead. Shouldn't you exit and just return and do nothing? That's another thing, maybe. Yeah, so we're constructing a tree. If we go out of bounds, we could return. See, the problem is it produces like worse code. So we got to try and figure out, like, is the worst code a problem for us performance wise? So we currently just min it. I'm not sure what a return will look like, because sometimes we've done some tuning and just changing how the for loop iterates does some things. And we've got to be careful about. I think this should be fine. Yeah, sometimes we might want to make sure that all threads are active as well, because we're depending on that behavior. Yeah, we're depending on all threads still being alive. Very difficult problem. Hey there, Top Tick Tomato. How's it going? Welcome, welcome. Since you have a different index, another thread could already be working on it, right? That's true. You would get more problems, wouldn't you? Yeah, it's. So we gotta, like, ideally, we want to catch these wrong indices in a rather elegant way. So we've really got to understand the code. So traversing down the octree, down. Oh yeah, this one goes down from the top. Find the cluster this thread owns, a 1/8 of, and see if a sphere or child node can be placed. Isn't she lovely? Look at that. So when you're saying this cluster node, you start at the root. That's another thing I'll think about is like the root node could. You've just got to make sure it's like if you only have one node and it's the root node and it's a leaf, it should technically be on the left hand side. Let's make sure we solve that problem at some point. But yeah, so in this case, we're then going to get the child one and then carry on. So 0 should be fine. So the question then is, given the child index, so that one could go out of bounds. Anyway, then you eventually reach your node. So after this, when you reach your node, are we dependent on, so what sort of threads are we doing? 4x4 by 2. By 2. This comment's probably wrong. Yeah, so we're getting 1/8 of a node. Wait. Yeah. Getting 1/8 of a node. Yeah. So go over all the edits and just see if it paints over that sphere and then puts a sphere down. So we're not caring about the neighbors. I think, oh, we do actually here. This bit right here. So we care about the neighbors being active. Excellent. So here's what we're going to do. We'll do a break. we want to say, okay, well, if the child node goes outside of those leaf, here it is. And that patches in the child index right there, yeah? Cool. So what we want to do is we're going to go, okay, if you've probably got to do an atomic load. Got to do atomics, man. So you probably want to get like a min and max, basically. Min node index equals negative atomic load E32, address of that, right? And then the max is positive non-leaf nodes. So leaf nodes are negative, non-leaves are positive. So we just want to say, oh, if the child index is less than min node index or child index, we could just do a clamp and do we could do a clamp and then do a comparison, but I don't know what is better. Right, because they come with like instructions now, like certain hardware. So maybe it might be better just do a clamp and do a comparison. I don't know. But anyway, we'll break here, and we need to set something to say, hey, don't do the next thing. So this we can put in a, and just say, you know, this is a sort of a safety check. Safety check for indexing this. Technically, we can do it above, right, for all of them. Okay, so if you get this, then what do you want to do? You want to not do any of this. And then we should need to do this check thing here. So what you want to be able to do is do like edits count, BC edits count, and then you basically mutate this, set that to 0. So we just want to say, you know, we have landed outside of the node somehow. So I guess we can put some debug printing in here if we want at some point. Somehow, sort of like, don't calculate anything. For this, we're trying to see if this sphere location, something like that. So this would set this to 0. So allocate child node will be false, so we'll never allocate a child node. Also, the spheres count. Sorry, the spheres count for this. The sphere will never get added for this sphere location in the cluster either. So this will never execute in that case. This could still execute. You'll copy. Yeah, you'll copy over. If you're the first thread, you'll allocate an array for the spheres. Then you'll copy all the spheres over. Every thread has to be active here. Every thread copies a sphere. Then if allocate child node is true, which will be false in our case, but yeah, it would allocate a child node for that location and all that jazz. Right, that's good. I like it. So let's compile. That should compile. Now we've fixed that problem. What is this doing? Oh, it's global. Right, what is this? Shift right. Design implicitly cast. I need an S on there. Cool. No. What is going on here? I don't have a shift right S. What is wrong? HMaths. The vector one, right? Oh. That's why it's ×3 version. We have that. Good, good, good. Cool, next one is outside shape. We missed that. LOD half dims. We've just messed around. I think it's just the half dims there. This code got heavily refactored. Right, what is this guy trying to do? Right, we need to say it wants to subtract 1. It returns the old value, but we want the subtracted value, so we subtract 1 from the result. But didn't I rename that to a slot index? Yeah, that was another piece of code. All of these need to be global. I cannot type. Cool. Okay, so we've got another one of these clamps. So this is, we've allocated something new. I'm just going to say this cannot mess up. Well, I guess it can. Technically, these could be set to something. Wait, did we even clear these? These need to get cleared. Constructor reset. So we didn't store it. So when we start constructing the volume, does this just do buffer access? That's alright, huh? Pretty sure. Where the hell is this stored? I'm pretty sure GPU shared. I have no idea where it is. Yeah, so it just does. It casts that into above, it does an access. So we should be able to do an assignment on that. It is wrapped though. Yeah, so we should be able to say this is going to be assigned 0. Assign 0 to the non-leaf nodes 1. I'm not sure why it's reading this. Yeah, so the midpoint cursor should be like the CPU should know, or we should know anyway based on it should be like a constant in memory. So if you've got 256 cubes, right? So 16 meg, so 16 million, right? 16 million possible spheres. Clusters are 2 by 2 by 2. So I think it would just be 128 cubed. I think that's right. See, I'm not sure if I typed that wrong. Let me just double check it. Yeah, good. So that's 2 meg. 2 million. 2 million times size of node. So yeah, we basically want to, like the number of leaf, it's a bit of maths to work this one out, but you've got like a number of leaf nodes. The number of possible leaf nodes. But you could probably work out from like a base. Like given the number of possible leaf nodes are the. Oh no, but it's that going. Okay, that's the highest. Right, so it's basically a MIP chain's worth going up. So I think it's like add half, something like this. You divide by 2 and you add that to it. So I think that might be right. Yeah, because you basically need to accumulate adding this divided by 2, this and that answer divided by 2, you know, just accumulate, add all of those all the way up to LOD 0. I think that's basically adding half. I don't know, it won't be. No, it will be, sorry. It means to add accumulate 64 cubed, 32 cubed, 16 cubes and so on. To add and accumulate all that, basically. Yeah, so I reckon we can find. It might be okay just to stick it in the middle. Like if you have one big buffer, all the leaf nodes go on the left, and all the non-leaf nodes go on the right, but I'm not sure. Let's see if we can work this one out. Let's jot these buggers down. So you've got you got 1, 8, 3 cubed. I could probably just search this on the internet. Yeah. Where did my browsers go? Did it crash? Weird, I don't remember that. Oh, the music obviously went, that's fine. Anywho. Cube numbers, yay. So 64, 125, 216, 343, 512. That's interesting. 512 is the cube root number. I see. So you got 8, misses 32, 64, misses 256, and you get 512. Right, so that means, I see, so 2048 will be a cube number as well. Whereas how many of these boys do we need? We need 8. Wait a minute. These numbers are way too small. What's the problem? 256 cubed. No, I need to punch these in manually. Yeah, I need him differently. That's alright. So I need squared. Yes, I need those two. I need 4. Okay, so I guess it's just this pattern, right? I think that's right. Um, 1, 2, 4. 1, 2, 4, 8. No, it can't be right. Right, that's correct, okay. So 16 cubed, okay, it's different, it's wrong. 32 cubed, okay. And then 64 cubes, and that's the final one we need, right? So if you add all these together, where is it? No, we need this one as well. 256 cubed, that's our highest res. Okay, so So if we add all these together times by the number of times by the size of a cluster node, that's the amount of memory we need. So if we add all these together, plus 209, 715, 2. Add 262, 144. Add 32. Add 196. Add 64. Add 8. Add 1. That's how many nodes that we need in total. So was it like adding half, like I was thinking initially? No. Not quite. Right, so that's how many nodes we'll need. So how do we know how many what's the maximum number of leaf nodes? Wait, is that the maximum number of nodes? That feels like too many, thinking about it. L0 is only going to have one node. Oh, yeah. So the maximum number of leaf nodes is this one here. That's the number, right? Your highest LOD is the leaf node. That's the maximum number you possibly have. Spreadsheet. Yeah, I haven't used spreadsheets since like school. Yeah, completely forgetting all that stuff. That's something that my dad used to do for a profession. He's been an accountant. So he uses the he really knows how to use a lot of Excel. Yeah, so that's the maximum possible number of leaf nodes, and the remaining is on the right. Okay, so it's a bit lopsided. It's more to the right, the midpoint cursor. I didn't realize that. So we can have these as constants. Oh yeah. (256 cubed). Then you want to basically say the maximum number of non-leaf nodes is sum 1 dot dot equals 7. No, that's not even it. One shift left. Days. To the power of 2. To the power of 3, right? So you're doing 1 to 7. If that's even understandable. So 1 to 7 to the power of 2 to the power of that, the other way around. 2 to the power of 1 to 7, right? Something like that. Let's write this more programmery. What's this, a custom engine? Yeah. So we're building some sort of custom tech where we're trying to render a ton of spheres, or as many spheres as possible. So we've just written out the LOD and clustering code, where it's all GPU driven, where we're building these custom volumes of 256 cubed on the GPU, but we're just trying to get it compiling, and then we've got to plug it in one by one. So we're just trying to sort of just get it compiling effectively. But let's go to passwords. Basically, there's a VOD channel here if you're interested in catching up. Some time ago, we made something like this. We've got model instances working, but we needed a way to make more of a complex model. Yeah, so we've got a sphere renderer that we're ray tracing. Again, so we've got 3 different ray tracers because I'm not sure which acceleration structure is the best. Yeah, it's all just custom game. Basically, we've not like the whole sort of engine, if you will, has been written from scratch. Using nothing but compute shaders. That's about it. Something like that. Right, this works more with my programmer brain. Value equals this sort of 4 range value plus equal 2 to the power of index to the power of 3. Right. That'll sort of work. Let's do something like that. Reads a bit better. Fine. Oh yeah, the number's not completely wrong. We need the sum number in it. So it's 16,777,216. Take away. That's the number of non-leaf nodes. Excellent. Oh, it's gonna be good. Right, so with this information, we'll be able to tell where the midpoint goes. And the midpoint, literally, right? We can set this up. Is equal to maximum number of leaf nodes, right? Because on the left-hand side is where the leaf nodes go. You just need to know... So what we'll probably do is we'll probably have the first section of the buffer of the cluster tree nodes buffer be for the build, and the rest of the stuff that comes after is purely for... They could technically be in different buffers, and that will probably be ideal, because then we won't get any... Yeah, we probably want them to be in different buffers, not gonna lie. Yeah, something we should probably do. Hey Spank Funk, how's it going? Someday I'll learn programming, learn 3D modeling in 2 years. Nice. Yeah, I'm back on my Corsair keyboard now because my fingers are feeling better. So I got my Corsair K9 or whatever it is, RGB 69 420, that one. Corsair RGB, this is my boy. Yeah, this one I'm using. It's pretty good, it feels good. It's got red switches. You know, it's that RGB stuff though, you know, as soon as the socket wall gets plugged on, it just lights up the room. But yeah, one of them. Excellent. Right, so I think this is a good place just to put a pin in it. So in the next stream, we'll get this all compiling, and then we'll start plugging in the first shaders. Yeah, it's going to be good. Good progress today. So next stream will be on Sunday at 6, probably at 6 p.m. GMT. And yeah, hopefully we hopefully we get something up and running. We might have to answer some of this. Yeah, the aim is to get something running. We have enough time, I reckon. So we might be able to we'll get this to work. Obviously, this is a free one, right? But maybe we can get this construct leaf nodes thing working, perhaps. Yeah, we'll see. Excellent. Right, let's find someone to raid. Nobody. Okay. What's up with these suggestions? I'm trying to move my mouse. There we go. Twitch. Good night. Take care, Jam on Toast. Good night, Akraz. Good to see you both. Thank you for coming by. Rightio. Have a good start to your weekend, everyone. I'll see you all on Sunday. And yeah, thank you for coming. Much love, right? Catch you later, guys.